Hi, so this is an introduction to regression. This is what we're studying in Algebra 2, and this video will help support anything that you might not have understood in class the other day, or if you even missed class and need to get kind of caught up with things. Regression is something you started in Algebra 1 when you started to talk about line of best fit. Regression is another term for line of best fit, but that's only a linear regression. So we are going to be looking at regression that goes beyond just linear regression. All right, so to do this, we're going to look at some data, and the data we're going to use is about baseball players' salaries. So I'm going to just jot that down here so we can kind of keep track of this. Players' salaries. Now notice that the units here for the salaries are in millions of dollars. So 1.0 does not mean a dollar, it means $1 million. And that's in 1980. And so what I want to say to you is that we probably need to change these numbers. Those years are really, really big, right? And if they're really, really big, then it's going to be very difficult for our calculator to calculate a regression equation, even if it's just a line of best fit, accurately, because there will be a lot of rounding error, and then there may be some regressions that won't even work because we're using this. So what we're going to do is we're going to define our x variable to be the years since, and you can pick 1975. Could have been the years from 1980 or the years from 1900 or anything like that, but we want to be able to make these a little smaller. So I'm going to say that this is year 5. Year 7, 1990 would be year 15, and in year 15 there were 2 of them. 91 is 16, 96 is 21, 97 is 22, 98 is 23. We've got 3 and 99, they're all 24. In 2001, we've got 26. 2004, we've got 29, and 2005, we've got 30. So instead of typing in the actual whole year, 1980, we're going to type in 5. And so you do that by going to your calculator, and you're going to press Stat, and you're going to select Edit. And in L1, we're going to go ahead and put in our X variable, our independent variable, and in L2 we're going to put our Y variable in. And we're just going to type all of these data in, and we're going to make sure that it's nice and even, because now I know this is not the bottom of our data, but when we get to the end we need to make sure that the 2 lists are even. If not, we'll probably get a dimension mismatch error, and that's something we just have to kind of go back and check for. Okay, so now that our data is in our calculator, we're going to go ahead and construct a scatter plot, because we need to look at the scatter plot in order to determine the best regression equation to try, or the best function model to try. So in order to do that, you're going to press Stat Plot. And you can get to Stat Plot by pressing, whoops, let me just pull this out of the way here a little bit. By pressing second y equal, and that's going to take you here. Then you'll notice that we're going to select plot 1. You need to make sure that it's turned on, and the reason it needs to be on is because otherwise your graph won't show up. A lot of times it'll appear to be blinking on. It needs to be solid, highlighted. The type of graph we're going to choose is the scatter plot. That's that first one right there. And our X list is L1 and our Y list is L2, because that's where we typed our data. Now we can change how you type these in, and we'll talk about that a little bit later, but that's where that goes. Now we want to look at the scatter plot so we can think about some functions that might work. So here is our scatter plot, and it seems that it seems like it's not in a perfectly straight line, although it could be if we just eliminate those couple of points. So I'm not really sure what we want to test for just yet. So let's make a list of some functions that might work. I'm looking at this in maybe linear. It's always a good one to check because it's kind of the baseline unless it's obvious that it's not a linear model. I think that looking at that reminds me a little bit, of an exponential function. And so it might be exponential. Or it could be cubic or even quartic or quadratic. But I'm going to try a quadratic, I think. And then, because I'm really not sure, I'm going to go ahead and test the power function too. The power function is nice because it models a lot of the other polynomial functions and the square root functions that we have that we can't really see anyway. So what we're going to do is we're going to test those 4 today. Now, of those 4, and normally you only need to pick 3, but of those 4, we're going to see which one is the best fit for our data. That doesn't mean that another model might not have been better. Maybe we'll find out cubic was better or some other function. But we're going to look at these 4, which seem reasonable based on what we're seeing here. You know, the linear, again, if we disregard those couple of points, it might appear to be very linear. But with those 2 points, we seem to have a curve, and so maybe exponential, quadratic, or power. And so that's what we're going to start with. In fact, we'll start by looking at the linear function. Now, before we look at the linear function, because we want to be able to see the correlation coefficient r and r squared, which is just the correlation coefficient squared, we need to make sure that our diagnostic has been turned on. So if you're using a TI-84 graphic calculator that's a plus CE, I know that you can press mode and you can scroll down to where it says stat diagnostics and you can toggle them on and off. But not everybody has stat diagnostics. And so another way to get there would be to press second 0, which takes you to the catalog. And then scroll down to where it says, where it says diagnostic on. You would select that, and that'll paste it right into your home screen as shown here. And then you can press enter to make sure though it says done before you're finished, because that's going to make sure that you can see the r and r squared values. So when we've done that, we want to actually see what the function equation would be, and in doing so we are going to press stat and we're going to arrow over to calc and we're going to select 4 for lin reg. And you can just scroll through and press enter. Your default will be L1 and L2. If you're using this operating system, on the newest, the TI-84 plus CE, you just kind of go through the list and arrow all the way down and then press enter when you get to calculate. But if you're using an older version, it'll just have stat or lin reg AX plus B, and the default is LM1, and you can just press enter and get your equation. So the equation that we find here is y equals AX plus B, but we're going to fill in our A value and our B value, rounding to the nearest hundredth. So let me move this. I'm going to put it here. Y is equal to, and if I'm going to round to the nearest hundredth, isn't that going to be, 0.97x minus 8, because that's going to round, And so that's our linear equation, and we're going to jot down r squared. R squared is 0.8406. Remember that r squared, well, the correlation coefficient r tells us how strong our linear association is. And that's really helpful to us. And sometimes that's going to show up for us, and sometimes it won't. But every single time we do a regression, no matter which one it is, we're going to see r squared. And so we're going to be able to compare that. So it might be a good idea for us to compare all the r squares, because those r squares are related to the r value, right? Just squaring them. So we're going to note that. The next one we're going to check, oh, wait a minute. There's something else we should check before we go on, because this is just the equation, this is just r squared. We also need to check something called the residuals. And the residuals are essentially your observed y value minus, oh, this is very messy. It's your observed minus the predicted y values. So in order to do that, we are going to actually look at what's called a residuals plot. And we learned in class today that a residuals plot should not, whoops, good gracious, I can't spell. A residuals plot should not have a pattern to it. If it does, it's probably not a good model. Instead, we want the values to be random. So in order to view that plot, we're going to go back to stat plot where we were before, and we're going to leave the same plot on. We're still going to use plot 1. We're still going to have it on. We're still going to have it set up for a scatter plot. We're even going to leave L1 correct the same, and we're going to change y from L2 to the resids. And they show up in your calculator every single time we do a regression. Every single time they become new. And so each time you do a regression, you should check your residuals before you move on. So the resids, you can get there, and we can just go scroll down here, arrow down, and change your resids by pressing second stat, which takes you to your list, all of your lists, which takes you to lists, and then you can select your resids list. Paste that in. Then you're going to do a zoom 9. And when you do a zoom 9, it's really called a zoom stat. Zoom stat, there we go. When you do a zoom 9 or a zoom stat, you're going to be able to see the residuals plot. And then you're going to look to see, is there a pattern? And that's our big question. Is there a pattern? And if there is, how strong is it? So looking at this, it's not a very good sketch here. That seems like a pattern to me, yes? So since it's a pattern, it means that maybe it's not such a great model. So the linear might not be a great model for this. So we're going to write clear pattern. We don't have to describe it, we just have to indicate that we've seen it. So we're going to continue with this as we look at the other 3 models. The next one we're checking is the exponential model. And you can see the equation is given to you. You're going to round to the nearest hundredth. So our equation here will be y equals 0.64 times 1.14 to the x. And r squared here is 0.9724. Now, if we were just going to compare the r squares, we can see that this is much higher than our linear model. But we still need to make sure that there's no pattern in the residuals plot. So let's take a look at that. And as we do, we see that this is less of a pattern. Do you see that? Resids are somewhat random, and that's what we're looking for in our residuals plot. We really want to see that they are random. Now ideally, if you look at this end, they are fairly scattered up and above and below the line. They are here as well, they're just much closer to the line. So this is clearly less of a pattern than what we saw before. Okay, moving on. After we've done the exponential, maybe let's try the quadratic. So on this one, I used a different calculator. My batteries had gotten low, but we can still see our equation. fairly easily. I'm going to just move this diagram up a little bit so we have room to write. And so we're going to get the equation the same way. This is going to be more complicated though because it is a quadratic regression. So we're going to have ax squared plus bx plus c. So this is going to become y equals 0.05 x squared minus 0.81 x plus 4.48 with an r squared value of 0.9652. Now if we're just looking at r squared again, this is better than, this is a stronger r squared than we saw for our linear model, but not as strong for our exponential. But now let's take a look at our regression, our residuals plot to see about this. Now as we look at this one, we'll see that this is also somewhat random, right? No clear pattern here. And we could say that the residuals are somewhat, somewhat random. So while there's no pattern, at this point we have two contenders, right? So let's take a look at the power model finally. And when we do, we get an equation here that says y is equal to 0.05 x to the 1.78 power. So not linear, but not quite quadratic, right? Because that would need to be a power 2 for it to be a quadratic model. But we get an r squared of 0.9258. All right. By the way, when we looked at the quadratic, did you notice that there was no r, just an r squared? Right. That does happen sometimes, so that's why a lot of times it's good to compare the r squared values. But looking at the r squared value, we see that that's a little lower. Let's just double check our residuals plot. And when we do, we see a clear pattern, right? So that means that the power model is probably not a good choice. So in summary, let's take a look at what we have. And I've just, on the next slide, we've got some notes, and let's make a decision. So for our linear, we saw that the r squared is 0.8406 and there was a clear pattern in the residuals. The fact that we're seeing that clear pattern in the residuals, I'm knocking that out right away. Exponential, we've got r squared is 0.9724 and our residuals are somewhat random. So we're going to hold on to that for now. Looking at the quadratic function, we have r squared is 0.9652 and again, our residuals are somewhat random, so we're going to hold on to that one as well. Let's check power. R squared is 0.9258, but there's a clear pattern in the residuals. So the fact that that's happening, that's out of there. So now we're down to two. We want to look at the exponential and the quadratic. Now, both of the residuals plot were somewhat random. One might have been more random than the other. It's a little bit hard to tell. But the best we can do, since we can classify them both as somewhat random, at this point, in order to make the decision about which model is the best model for this function, for these data, we would need to look at a r squared. And we see that the exponential function has an r squared that's a little bit stronger than the quadratic. So the best model here of these, or the most appropriate, I think I want to say that instead, the most appropriate model is going to be exponential. Whoops. Alrighty. Hope this helps.